Hello everyone. Welcome back to Exploring Quantum Physics. I'm Charles Clark. And now we're going to wrap up the connection between the angular momentum of the Runge-Lenz vector that we saw in a previous lecture and use that to describe the spectrum of the hydrogen atom. So I hope you remember
from lectures of the past week, we derived this the constant of motion for the hydrogen atom, unusual type, the Runge-Lenz vector, which is really the cross product of the momentum and the angular momentum and the radial vector, and this lies in the same plane as the radius, same plane as the position of the momentum classically, and it serves to define the elliptical orbit that the electron and the nucleus make about the center of mass. Well, the classical definition is asymmetric in P and L, and precocious young scientist Wolfgang Pauli devised a symmetrized form, and he takes the mass out and puts it in a different area. So as you can see, this M vector that Pauli derived is identical up to an overall constant to the Runge-Lenz vector that we derived, but it has a nice symmetric form that is required by quantum mechanics. Well, I invite you to give your opinion on that in the in-video quiz. Now, the central result found by Pauli, and it seems mysterious and miraculous to me, has to do with the commutators of the angular momentum operator and the Runge-Lenz vector. So you have already derived this, and since M is a vector valued operator, this is a consequence. This is the common commutator that applies when the angular momentum operator is applied to any vector. But now here's the new one, and I am not going to go through a step-by-step derivation because it's a lengthy one, but as you can see from the mechanical point of view, this just involves it now involves the M. The M has products of P x P. There are triples of momenta and coordinates in its expressions, so it's lengthy. But when it is done, this is the answer. And as we'll see, these identities make it possible to find the bound state energies of all solutions of the hydrogen atom without actually solving the Schrödinger equation. Now, first I'm going to talk about the spectrum that's associated with the angular momentum operator itself. It's very important. And I'm going to outline the derivation here, just because, for the interest of time. But it's something that you can do yourself. I've done it. And Zach Rains has written up some nice notes that sort of take you step by step through that. So the first observation is that since L3 and L squared commute, and there's nothing important about L3 here, but it's we know that L3, L1, and L2 do not mutually commute, though each one of them commutes with L squared. So we're going to pick, just by convention, we pick L3 to be. We're going to make eigenfunctions that are eigenfunctions both of L squared and of L3, because we can choose to have eigenfunctions that have both those eigenvalues simultaneously. So we'll call these, by convention, Lm, and L3 Lm
is just the eigenvalue denoted by this. Now, it will turn out that L is equal to 0, 1, 2, and so on, integer, and then M is equal to minus L plus 1, etc., up to L. But for the moment, we'll just leave it undetermined like that. Okay, now, in order to prove the spectral property, this is the spectral property of the angular momentum operator. It's straightforward to prove it if you define these two operators, L plus and L minus. These are sort of like, they resemble to some degree the creation and annihilation operators of the harmonic oscillator problem. So you can readily verify this identity because, we're just saying you've previously established that, for example, L3 commutator L1 equal IH bar L2. So it's quite straightforward to verify that this identity, which says, for example, when you take this and you now say, all right, let's apply L plus or L minus to this Lm. Is it an eigenstate of L3? And indeed it is, but it has its its eigenvalue of L3 is increased by plus or minus 1 times h bar. So, in other words, if you start, whatever this state may be, Lm, if you start with Lm, then you get a sequence. So this is the value of L3 here. You get a sequence of equally spaced values of L3. So this is an example of a ladder operator. It's somewhat analogous to the creation and annihilation operator. Generates a sequence of eigenstates with equally spaced eigenvalues. Well, the full analysis requires that this sequence terminate at some point, because if L squared has a fixed value, that means there's a maximum value of the maximum eigenvalue for any one of its components, and that yields that analysis yields the following result: that the spectrum of the angular momentum operator, it's L squared, the eigenvalues of the form L times L plus 1, where L is any non-negative integer, so 0, 2, 6, etc. Now, there's a widely used system of eigenfunctions of the angular momentum operator. These are called spherical harmonics. Here's an appropriate reference for their properties, and they're expressed in spherical coordinates. So basically, if you have a function in three-dimensional space, the spherical harmonics are used to parameterize the angular dependence. So by convention, this is x3, the z coordinate. Phi is the azimuthal angle, and theta the conventional polar angle. And here is an image that shows the various so for L equals 0, there's m equals 0 only. For L equal 1, there's m equal plus 1, 0, minus 1, and so on. Now, I think it's useful to keep in mind that YLM is basically a polynomial of degree L divided by r to the L. So all these functions, I mean, their expressions can get pretty complicated, but you can always think of them as polynomials. So, for example, y0 is 1 over root 4 pi. It's just a constant. It's just a constant function. Y 1, 0, and minus 1 are, well, y10 is proportional to cosine theta, which is, so it's proportional to z over r, and y1 plus or minus 1 are proportional to x plus or minus iy over r. So they're the things that the most problems that you encounter just deal with fairly small values of L, whereas the spherical harmonic functions are rather simple, but they're a very powerful set, and they're widely used in many applications in physics and mathematical analysis. Now, it turns out, to get back to the angular momentum and Runge Lenz vectors, these operators L and M together, let's just think about the bound states of hydrogen for the motion, together they're the generation, they provide the generators of a rotation group in 4 dimensions. So the hydrogen atom has an internal symmetry which is like the symmetry of an object that has particular transformations under rotations in a space of 4 spatial dimensions. It's quite extraordinary that such a deep relationship exists. Now, I don't think it's possible to make a interpretation of that 4th spatial dimension that's something that exists like one of the 3 spatial dimensions with which we're familiar. But it is striking that this very basic dynamical system, the hydrogen atom, the simplest atom, has this very rich and symmetric structure with a high degree of degeneracy. So for a given value of principal quantum number, let's say n is equal to n plus L plus 1, there are n squared states with the same energy. So this degeneracy receives, I think, spectacular confirmation in this data from the molecular cloud that we saw in an earlier lecture. So this frame shows absorption by states in a molecular cloud with an n value of 600, and there are basically something like 300. In this region, there are 350,000 states with the same energy, and there are 350,000 states in this vicinity, and you see sharp lines here, and these are, according to our best understanding of the system, those states are all equally populated. So you're seeing this sharp ringing. All of these hundreds of thousands of states are making transitions at exactly the same frequency. It's really quite a remarkable thing. Indeed, without this high degeneracy of these are actually carbon-like atoms with a highly excited electron, so they're hydrogenic. Without that exact degeneracy, we wouldn't see these signals at all. So we're going to conclude for the moment there, and then proceed in the next lecture with some discussion of more applications of angular momentum. Hope to see you then.